In the last few videos, I've been building up intuition about sampling distributions, and the payoff is going to be in today's video where I talk about interval estimation, in particular calculating confidence intervals. So we're thinking about estimating the population mean, E of y, for a particular variable, such as home prices. We have a sample, and so we can calculate a sample mean, m of y, and we're going to use that as our best point estimate of the population mean. And the word point here simply means that it's a single number that we're using to estimate our population mean. But because we just have a random sample from the population, our sample mean is unlikely to match the unknown population mean exactly. It's going to be off by a little bit. So how far off might it be? Well, it would be nice if we could quantify that uncertainty. And the way that we quantify that uncertainty is with a confidence interval, which is centered at the point estimate, and then we add and subtract an amount of uncertainty to give us an interval. So an example is an 80% confidence interval for the expected value of y, the population mean, in the home prices application is a point estimate of 278.603 plus or minus an uncertainty of 12.893, and if we evaluate that, it gives us an interval going from 265.710 up to 291.496. And so what we can say is that based on this data set, we are 80% confident that the population mean home price is between these two numbers. And we typically would round at this point. So to the nearest $1,000, we can say that we are 80% confident the population mean home price is between $266,000 and $291,000. So that's an 80% confidence interval. It leaves quite a bit of room for error, 20%. And so in practice, you'll find that 90% and 95% intervals are more common than 80% intervals. But we're using an 80% interval here just to illustrate the process. So let's think about a 90% interval for a second, and whether that's going to be narrower or wider than an 80% interval. So if we're wanting to be more confident, 90% confident rather than 80% confident, we're going to have to widen the interval so that we can be more confident that the population mean is in between the endpoints of our interval. So as you increase the level of confidence, your interval is going to get wider. So let's work through how to calculate a confidence interval, and we'll work with 80% confidence interval. So we can make a probability statement that says the probability that a t-distribution with n-1 degrees of freedom is in between minus the 90th percentile up to plus the 90th percentile is equal to 0.8. And that 90th percentile is coming from a t-distribution with n-1 degrees of freedom. So that might look a little bit odd at first sight because we're doing an 80% confidence interval, but we're using 90th percentiles. So why is that? So I'm suggesting draw a picture and we'll discover why. So let's draw a picture. So let me draw a t-curve. Okay, it looks roughly like a normal curve, but with slightly fatter tails. Okay, and then I'm going to mark off an 80% interval. Okay, so this would be the lower bound of the interval, and this would be the upper bound of the interval. And so I'm saying that we've got 10% and then 80% and then 10% up here. So 10% in each tail and 80% in the middle. That's an 80% interval. So where's the 90th percentile coming in? Okay, well over here at the upper bound, that's the 90th percentile. And why is that? Well, it's the number such that 90% is to the left and 10% is to the right. So you can see 90% is to the left because we've got 10 in the tail and 80% in the middle, so 90% is to the left. So that's why we need a 90th percentile for an 80% confidence interval. Next step is to plug in our formula for this random variable tn minus 1. Okay, and it's the sample mean minus the population mean divided by the sample standard deviation over root n. So what we do is we plug this expression up here into this probability statement. And then we do a bunch of algebra because we're trying to isolate e of y and move everything else onto the other sides of the inequalities. Okay, I'm not going to go through all those steps. It's just a little bit of kind of tedious algebra. We end up isolating e of y, the population mean, and then on the other sides of the inequalities we've got things that we know or that we can calculate. So in other words, that 80% confidence interval can be written as sample mean m of y plus or minus the 90th percentile of the t-distribution with n minus 1 degrees of freedom times sample standard deviation divided by root n. So that's the formula for an 80% confidence interval. What would the formula look like for a 90% confidence interval? So just think about that for a second. Okay, everything here is going to be the same, m of y, s y, root n, except for the percentile. So if we go back to our picture, what would our percentile be if instead of a 80% confidence interval we've got a 90% confidence interval? Okay, so let's suppose we've got 90 in the middle now. Okay, and then we would have to have 5 in each tail. Okay, so what percentile would this be? It would be the 95th percentile. Okay, so the formula for a 90% interval would be the same as this, except the 95th percentile would be in the formula. Okay, so you ought to be able to figure out which percentile you would need for any type of confidence interval. So let's work through the calculation for the home prices data that we've looked at before. We can calculate the sample statistics using statistical software. So here I am over on the left using R, and we've got a sample mean of 278.603, standard deviation of 53.8656, and we're doing a 80% confidence interval, so we need the 90th percentile, and the 90th percentile is given over here using the QT function in R, and it's 1.311. And then I just put all those numbers together into the formula, and here's the calculations over here on the left in R. The uncertainty is the t percentile times the standard deviation over root n. That comes to 12.893. And then if I take the sample mean 278.603 and plus or minus that uncertainty 12.893, we get 265.710 up to 291.496. And we just quickly run through what the calculation would look like for a 90% confidence interval. So remember, everything's the same except we have a 95th percentile instead of the 90th percentile. So the 95th percentile is 1.699, and so you get the expression 278.603 minus 1.699 times 53.8656 over square root of 30. That gives you 261.895. And then the same but with adding on the uncertainty instead of subtracting it, and we get 295.312. So that would be a 90% confidence interval for the population mean. Just quickly in R, rather than doing the whole calculation kind of longhand, we can use this t-test function, and that will give us, let me just run that so you can see it. So down here we get quite a lot of output, but in particular right in here we get an 80% confidence interval. Okay, and that's because I said conf.level equals 0.8 in here. If we did a 90% confidence interval, we would get those numbers there. So these values that we're getting using the t.test function, they're not matching our calculated values exactly because we had a little bit of round off error when we did our calculation. Okay, so that's how to calculate a confidence interval, or how to use statistical software to calculate it for you. What's the interpretation? So loosely speaking, as we've said before, we can say based on the data, we're 80% confident that the population mean home price is between $266,000 and $291,000. So that's the easiest way to interpret the interval using this wording here. You'll note that there's no use of the word probability in here. Okay, confidence intervals are always about being confident that the parameter that you're trying to estimate is in between two numbers. We don't ever say anything about probability here. If we want to understand a little more precisely what this means though, because this is kind of a very loose statement, what it means is that if we were to take a large number of random samples of size 30 from this population of sale prices, and if each time we took one of those samples we calculated an 80% confidence interval, then considered all of those confidence intervals together. Okay, so we've got lots of samples and so we've got lots of confidence intervals. Then 80% of those confidence intervals on average would contain the population mean. Okay, that's a more precise definition of what a confidence interval is. You can picture this with this diagram at the bottom of the slide. So here I've imagined taking 10 samples and calculating an 80% confidence interval for each sample. So up at the top, my confidence interval is, and imagine a horizontal scale here. So it's going from this value is the lower bound, and this value is the upper bound. And then the second sample goes from this number up to this number. The third one goes from this number up to this number, okay, and so on. So these are all my intervals, and I'm just doing a thought experiment here. I'm imagining that the population mean is given by this vertical line here. So this is where this population mean is that we're trying to estimate. In practice we would never know this number, but I'm imagining that I can show it here because I'm just doing a thought experiment. And we can see that sometimes the population mean is within the interval. So it is for this first sample, and it's in the interval for the second one and the third one and the fourth one. But the fifth one, the interval is over here, but the population mean is to the left of it. So it actually, this confidence interval misses the population mean, which is, it's not good. Okay, ideally we would want our confidence interval to cover the thing we're trying to estimate, but in this case it misses it. But in the next one it does, it is in that interval, and for the next one it's inside the interval, and this one it misses again, and then the 9th one it's inside, and the 10th one it's inside. So for these 10 samples, it looks like in 8 of them the population mean was inside the interval, but in 2 of them it wasn't, this one and this one. And so that's what it means to be 80% confident, because 8 out of 10 intervals contained the population mean here, and 2 of them didn't. So that's a more in-depth explanation of what a confidence interval means. So it's nice to be able to understand this, but in practice, when you're interpreting confidence intervals, you pretty much want to stick with this interpretation up here, because this is the one that's easier to say, and but what's going on behind the scenes is this interpretation here. So I've reviewed confidence intervals for a population mean and given you background into how the formula is developed, and then how to use the formula to do the calculations in practice, and then talked about how to interpret the resulting interval.